We've seen where adding too many features is going to be a problem. And this makes sense because one of the problems we've seen so far is that we don't want our model to be too adaptive. We don't want our model to fit too closely to the training data, because at a certain point it's no longer learning from the patterns, finding structure. It starts to fit the noise in our data set. We don't want that to happen, but that's gonna happen if our model is too adaptive. As we increase the number of features, we're going to increase the number of possible ways for the model to adapt to the data. We see this very clearly in linear regression. Each feature is going to result in a beta coefficient. So as we increase the number of features, we increase the number of degrees of freedom the model has to play around with to adapt to the data. So let's discuss techniques we can go ahead and do such that we can prevent our model to be overfitted. We don't want our model to be underfitted, but we also don't want our model to be overfitted. Let's consider the idea of regularization. Okay, so right here we have the cost function. So let's consider the cost function for standard linear regression. In standard linear regression, you're trying to find the beta coefficients to reduce this cost function. This cost function is the mean squared error, or the sum of square errors. But using this metric, or using only this term in our cost function, is going to be a problem. Because at the moment, we're saying, hey, the best model has the lowest cost function for the training data, the lowest mean squared error for the training data. But we don't want a model to simply just try to minimize this mean squared error, because we understand we're going to have overfitting. So it's going to add an additional term to our cost function. This additional term is going to be the regularization parameter, expressed right here. So now our cost function has two competing terms. We want to reduce the mean squared error for our data, for our training data, but we're going to incur a cost if those beta coefficients are too large. Notice this cost is proportional to the sum of square of the beta coefficients. So if we have a lot of beta coefficients and their magnitude is very large, they're going to incur a very large penalty. And the strength of this penalty term is governed by this alpha parameter, this regularization parameter in our model. Now, one way you can view regularization is the idea of regulating markets. That's one of the ways I like to view what's going on here. Some people advocate that for markets there needs to be some amount of regulation. You can, fight day or night talking about the extent of those regulations. But the argument there is that these markets, we need regularizations, because if not, then the companies will put profits over people, profits over society, profits over the environment. It's going to be too short-sighted. It's going to go strive to increase the number of profits at the cost of other things. So we need to apply some regularization. Same thing here. Without this regularization parameter, the model is going to be concerned about minimizing this sole parameter here, this sole term in the cost function, which is the error with the training data. But now we say, yes, that's important that you want to reduce, but you should also consider the fact that you will incur a penalty when your beta coefficients are too large. So you want smaller beta coefficients. And this term here is going to prevent our model to be overly complicated. And the reason why it's going to prevent our model to be overly complicated is, let's consider our linear regression model. So beta naught plus beta 1 times x of 1 plus beta 2 times x of 2 and so forth. If there's a lot of coefficients, the model is overcomplicated. And one way to reduce complexity in the model is, let's reduce the volume of these beta coefficients. You could think of these beta coefficients represent how much impact a feature contributes to the model, to the predicted value, this y hat value here. So if we're able to reduce the beta value for a feature, yes, it's still in the model, but its impact, its contribution has been minimized. As we set beta, we push beta closer to 0. So yes, it's still there, it has some impact, but it has a very minor impact. So that's what this here term represents. You want to reduce this penalty And the way you reduce this penalty is you reduce the beta coefficients. You reduce the impact of your features to the predicted value. Now let's consider the fact here, if I have a model that's overfitted, should I increase alpha or should I decrease alpha? If our model is overfitted, that means it needs more regulation. So I need to increase alpha, have a less complicated model. On the other hand, if I'm underfitting, then perhaps I need to reduce the alpha term. Now what we have here written out, this cost function, this is the ridge model that we've seen so far that we played around with for illustrative purposes. This is what's going on when we use the ridge model. The ridge model is going to adapt the cost function of the linear regression to include this regularization term. Now what's so special about the ridge model is that the form of this regularization, we're summing the squares of the beta coefficients. So if this regularization term is proportional to the sum of squares of the beta coefficients, the model parameters, that's called ridge. There's also another model we can use that's going to do regularization that's based upon linear regression, and that's called lasso. And in lasso, we are taking the absolute value of the beta coefficient, the sum of the absolute value of the beta coefficients. Let's explore these two models in scikit-learn. So from linear model, let's import ridge and lasso. Do the customary train test split. When you're doing regularization, you need to scale your data. Why do you think we need to scale our data before we use linear regression, before we use these linear models that have regularization? What about them indicates that we need to scale them, scale our data set? Well, the reason why we need to scale the data is because of this regularization term. In order for this regularization term, we see how it's treating all the features equally. Then we got to make sure that all our features have the same scale or have very similar scales. So because of this regularization term, it's imperative that we scale the data. So we'll do that for our analysis. We'll scale the data. And what we're going to do here is we're going to have a for loop. We're going to iterate through a range of alpha values. We're going to use a log space. When we're tuning our model, when we're deciding what's the best alpha value to choose, it's best to use a log space. So we'll create a log space. We're going to iterate through. Of course, we would do this something like grid search or randomized search, but we're doing this manually for visualization purposes, for demonstration purposes. And we have these parameters here, which are lists, and we're going to store the model's coefficients for the ridge and lasso. So let's go ahead and run this block of code here. We're also going to print out the test error, so that ran really quickly. So we see that linear and ridge did just as well, and lasso did slightly worse, but comparable. So once we've generated all the beta coefficients for various versions, for various values of alpha, let's visualize the results. So we're going to do there. It's a little hard to tell here, but it looks like, the scale isn't great. But what I want to point out here is that as the regularization term increases, the R-squared value for the lasso has dropped, more so than the ridge and the simple linear regression. And one of the things I want to point out here that you might be wondering, so what is lasso doing differently than ridge? Besides the fact that lasso is going to have a sum of the absolute value of the beta coefficients opposed to the sum of squares of the beta coefficients. Well, one of the interesting properties of lasso is that lasso can automatically do feature selection. Regularization is going to push those beta coefficient values closer to 0. But with a model like lasso has a capability of pushing those beta coefficients all the way down to exactly 0. If a beta coefficient for a parameter, for a feature in the model is 0, is it even there? No. If a feature has a beta coefficient of 0, then it has no impact to the predictive value. It's like it's not there. It's like it's not included because it has no impact. It's set to 0, that term disappears. So that's the thing about lasso. Lasso has that capability of reducing those beta coefficients all the way down to exactly 0. Ridge, on the other hand, is going to push those beta coefficients close to 0, but not exactly to 0. And that's the difference with lasso. It has automatic feature selection. Lasso will automatically, if the alpha value is strong enough, can go ahead and set some of those features down to 0, eliminate them from the model. It's going to plot our results in a different way. So here we have the different beta coefficients as a function of alpha, the strength of regularization. So remember, as I increase alpha, what I'm telling the model when it fits, when it trains, says it's more and more important to have a simpler model, more and more important to truncate, to reduce those beta coefficients at the cost of fitting the model to the training data. Remember, we have two competing terms in our cost function. So I want to point out here, there's some drop with the ridge model. Of course, linear regression, there's no change. Who we see here in the lasso, where some of these features are going to get pushed down all the way to 0. And notice that if the model had a very small value for beta, it takes a small amount of alpha to set the value to 0. But if we have a strong value of alpha, a large value of alpha, is able to push some of these more important values all the way down to 0. Which makes sense, because if I go back to the cost function, and if alpha is very large, extremely large, then that means that it's better just to minimize that second term at the cost of fitting our training data. Right, let's use our lasso model and let's look at the coefficients. And there you go. So these are our two remaining coefficients. We go ahead and look at the beta coefficients from using lasso and notice things like average number of rooms, average number of bedrooms, populations have been set down to 0.